I need to stretch some metallic membranes almost to the point where they rupture. They're for a special project I can't talk about yet, but I am able to share how I made the membrane stretch-in fixture.
Be careful with that foil, it's only 10 micrometers thick. That's 4/10 for any imperialists in the room. The tensile strength is only about 200 megapascals.
Dag nabbit, Muskie. Foiled again.
I've lost count. Is that the 7th or 8th time you've messed it up so far?
As AIMEE said, the foil's a copper alloy and it's about half the thickness of household aluminium baking foil. I need to stretch it beyond the elastic limit so it work hardens and becomes extremely flat. It has to be stretched radially rather than linearly, so I designed a fixture to clamp the foil over a void and then force a radius polished stainless steel piston against the foil to stretch it in all directions at once. First step's making the piston from a piece of 316 stainless bar. I don't know how well it'll machine and I'm trying a new YG1 insert from Cutwell that's designed specifically for good performance on stainless. I didn't take a deep enough cut off the face, so I'll try some more optimistic cuts to see how it behaves.
It's not dumping much heat into the workpiece, although the chips aren't colouring up like carbon and alloy steel does. I can see there's a bit of tool deflection. Those spirals in the machined surface are a dead giveaway.
Taking 4mm off the diameter at 2mm depth of cut seems to break good chips so long as I keep the feed rate high. I'm not over impressed with the finish though, it's definitely nothing like the finish I can get on 4140 and tool steel using a similar depth of cut and chip load. Useful data for a future application anyway.
Ooh, nice chips.
Right, now I'll face off using a polished insert intended for aluminium, as I know they'll give a very good finish with light cuts in stainless. I need to hog out a pocket into the face of the bar, so I'll drill it with some cobalt split point drills to 6mm, then 12mm, and then move to a 16mm 2-flute end mill, and finally a 4-flute 20mm roughing end mill. As expected, that's a reasonably good surface finish. That's a nifty sheepskin taper wiper available from all good stores. I'm using the big Jacobs ball bearing chuck on an MT3 taper. Now this next step is going to alarm some folks, but it's a safety measure because I'm going to be doing something sketchy next. Disclaimer time. Do not copy what I'm doing here, as it is all ill-advised.
I do love this comedy-sized centre drill. It must be half an inch diameter.
Yes, I know I shouldn't be using them in a drill chuck, but this material isn't grabby, and I've got one foot on the emergency brake. The tailstock doesn't have a drawbar, so even if it was in a collet chuck, it could still grab the chuck out of the MT3 taper.
Well, that was surprising. That 4-flute high-speed steel roughing end mill cut the stainless very cleanly with no chatter, unlike that coated 2-flute job which screamed like a banshee doesn't. This little 12mm boring bar came from Art Euro Trade. It was very low cost, perhaps £15. It's using a CCMT 060204 insert, which is the usual polished and uncoated carbide for aluminium that I like. Now for a trick I learned from my dad. When he had a scrap end mill or radius tool with one or more broken teeth, he'd bring them home to use on his little lathe. This is an almost new 4mm radius cutter. It should do very well as a form tool to make the smooth radius on the edge of the piston so the foil can flow over it. I'm moving the tool radially and axially so that I don't get any chatter. If you just try going straight in, the cutting area is so large that the thing yells like a yelling thing. I'm being extremely careful about not allowing the Scotch-Brite to get into a position where it could wrap round the workpiece or catch on the lathe. Polishing fine details like this is potentially very dangerous indeed. I use small pieces of abrasive, tiny bits of alumina paper or small blocks of Bright Boy or Cratex, and I stay highly aware of what's going on. That's shorthand for, if anyone feels the need to yell at me in capitals about how I'll definitely lose body parts from doing this, please don't bother. Troll's gonna troll. Off camera, I repositioned the tool to round over the top and inside edges and then gave it another polish, finishing with some extremely fine diamond paste. In fact, I think it's safe to say, I think that'll do. The piston needs an M6 threaded hole through the axis. I'm going straight in with a 5mm cobalt split point stub drill from Drill Service, as I've got plenty of tolerance for concentricity. Those drills self-centre really well. My dad used to hand grind split points that were a work of art. He was a tool and cutter grinder after all. Sadly, it was a learned skill and not a genetic trait, so I haven't inherited that ability, whatever Mr. Lamarck says.
Fair to say you're almost as bad at grinding split points as you are at TIG welding.
That lovely earwax on the tap is CT90. It's an unattractive shade of brown but sticks like a thing that doesn't come unstuck. It also makes taps glide through even quite horrible material. Marvellous. And that's my lovely Starrett 93B tap wrench. It's an absolute joy to use. If I remember, I'll put a link in the description. The tap's a spiral flute M6x1. It might be a Volcal. The length of the piston isn't a critical dimension, so I'm aligning the right edge of this 1.5mm MGMN parting tool with the top of the curve, then taking an extra 0.5mm that I'll machine to size later. So far so good. I'm quite liking this 316. It's got a reputation for being a bit tough, but actually it's machining beautifully. Right then, it's fixture time. I'm making a mandrel from brass facing it, then fitting an M6 thread for the piston to screw onto so that I can machine the back flat. That's an M5 stub drill for the M6 thread. I drilled and tapped the hole rather deeper than strictly necessary. I'm fitting a short grub screw or set screw down the hole to act as a stop for a longer grub screw. I could have jammed a bolt in and then sawed the end off and machined it to length, but the box of stainless grubs was nearby. Luckily, concentricity is not important because I'm only making the back flat. If I'd done this properly, I would have single pointed a thread on the end of the solid bar. Well, I think that passes muster. It'll get a final polish before it's actually used, but I think that's nearly good enough. I'd be really grateful if you could click the like button. It makes the YouTube algorithm ever so happy. And then it'll show this video to loads more people. This is my splendid chuck stop from Edge Technology, links in the description. The parallels are able to move a little to ensure they're flush with the chuck face. I like it because it's quick to deploy and doesn't need any changes to the chuck. This part's going to be the clamping ring that holds the foil membrane down.
We start by facing it off for no historical or cultural reason at all. Is that better?
It's time for a huge apology for the next 39 seconds of blurry video. My inability to operate a camera is legendary. The focus was probably fine for anything buried 30 feet below the floor. I can't reshoot the footage, but if I miss it out, there's a gap in the story. Anyway, that's the body and clamp ring surfaced and faced. Next steps to clean the faces with acetone and use little high viscosity CA glue, or superglue if you prefer, to fix the clamp ring to the body so I can machine them and ensure they remain concentric.
What are the chances Neil's thumb will be glued to the workpiece? Where are your nitrile gloves?
Well, the cap is a bit wobbly, but there's more than enough material needs removing. The seam's almost invisible. I like the way the glue doesn't run and drip like some CA glue does. I've lost count of the number of pairs of jeans that I've ruined. That's a decent finish as well. Now I need to drill and bore out the centre of the body and hope the cap stays glued in place. Fingers crossed. Well, actually not. It makes it very hard to operate the lathe. I'm taking easy steps up to 11.5mm drill, and then I'll use a 12mm machine reamer to finish the rear bore. Ominous foreboding, as Quinn would intone at this point. The front part of the body and the ring need opening up to about 35mm, but although my confidence in that glue line is rising, I'm still going in steps. 17mm first, then 20 and then 25. That 25mm drill does look a bit brutal for that small part, and it's singing a bit too much for my liking, but it's sharp and it's removing 2.5mm per side without breaking the glue line. Also, I've got excellent 3M ear defenders, hashtag not sponsored. I'm not going to risk using my giant drills. I've already used up my entire store of good luck with that 25mm, so I'll remove the rest of the stock using a boring bar with the same CCM T060204 insert that I used on the stainless piston. The tolerance on this hole doesn't justify the use of my SPI 25 to 33 point bore mic, but I'm doing some tests of tool deflection against feed rate, depth of cut and spindle speed in my never-ending quest to hit the dimension of every part I make smack in the middle of the tolerance range, so any excuse to gather a bit more data. It also means I can check the calibration of the ancient 1980s new all digital readout on my equally ancient lathe. The DRO uses a lot of TTL chips, doesn't have a processor and it's very analogue. It's still going strong after 40 years. If you don't know what TTL is, try asking a techie who was born in the 50s. The hole needs a proper chamfer on it rather than just deburring so that the piston will drop straight in. This new hull uses original Sperasin scales, which are a marvel of old tech, working rather like a linear variable differential transformer, but using a stack of precisely machined ball bearings, measuring the phase difference between an incident and an induced oscillation. Damn clever stuff. I'm leaving the ring glued to the body so I can drill the bolt circle in one setup for the 10 tapped and clearance holes. Spoiler alert, close your eyes and count to 5 if you don't want to see into the future. You didn't really close your eyes, did you? Safe to open them now anyway. This little part screws into the piston and acts as a pusher and a rough alignment bearing. It needs an M6 thread on top to fit into the piston thread. I'm not single pointing it as it's not a high tolerance part. The split die will do fine. A quick check to make sure everything fits and then we can part it off. Now it's time to put the dimple in the end of the pushrod and make all the other parts, but that'll be in part 2, which will be up there quite soon.
Ooh, I love cliffhangers.